Yeah, so some of what I'm about to say may overlap a little bit with what I talked about earlier with the audio capture side, and I guess that's to be expected because you can't completely separate out what you're doing with in terms of audio capture and audio rendering, as one directly implicates on the other. But I'm going to be kicking this off, and then I'll hand over to my colleague Holger, who will continue with the rest. So we'll be looking at what is format agnostic audio rendering, and then I will introduce a sort of object-based approach. We'll have a look at two sound field descriptions, being wave field synthesis, and at this point I'll hand over to Holger Kropp, who will deal with the higher order Ambisonics, the audio capture, some TCP IP stuff, and some reproduction things. So you've got that to look forward to. Okay, format agnostic audio rendering. I think we said several times today that FascinatE project is essentially about capturing the scene. In an audio sense, we need to capture the spatial scene. We need to know what audio is happening and, importantly, where it's happening. So from a rendering point of view, if you're a lady in red walking around distributed loudspeakers, you want those speakers to reproduce the correct signals so that you have that sense of being there. You have the sense that there's an actor standing there and there's a bus over in this corner about to run them over or something, I don't know. But you want to have the audio to match up perfectly with the video, which is important to some extent with today's technology, but when you're looking at interacting with content, it becomes even more paramount. And it's important that the way we deliver the audio is in a way that can be interacted with and adapted at the reproduction end. And as I said, this obviously has implications on how we capture the audio. And the way that we're putting it forward is that we want to capture audio objects, and we also want to capture the sound field, which is something that we'll talk about in a few minutes. So when we're looking at format agnostic audio, we have to deal with the fact that every single user has a different loudspeaker setup, and it may be that people even have a loudspeaker setup that doesn't exist in theory. Maybe they're trying to do 5.1, but they've got loudspeakers in miscellaneous locations, over a door, behind a sofa. And so everybody's need is different, essentially, but we want to provide people with the very best possible audio rendering that we can. And as I've mentioned previously, we want to basically provide the renderer with all the jigsaw pieces. What does the renderer need in order to put this audio scene back together and reproduce over whatever loudspeakers they've got available? So there's a bit of encoding in there. We need to encode our sound field in a format that can be then deconstructed, and we also have to deal with deconstructing it and rotating it, etc. So currently things are done generally by saying, well, I want this broadcast to be a stereo broadcast. So you basically, the producer does his mix and feeds out 2 channels of audio, or 5.1, and you dish out your 6 channels of audio, etc., etc. But for a format agnostic approach, we want to look at an object-based audio. So when I mean object, I'm saying that we want to, rather than try and produce a different stream for each possible reproduction format, a 2-channel stereo, a 5.1, a 7.1, or crazy 22.2 or anything, rather than sort of doing a specific mix for that, we want to provide those all the information, the sound field, the audio objects, so that it can be reconstructed for that sound system. So it's a fundamentally different technique. It's a bit of a paradigm shift. We're not looking at this kind of, it's this loudspeaker, but it's rather kind of positioning the audio sources accordingly. And so we're providing the renderer with all this information, which allows us to then interact with the scene and it to change accordingly. So I've mentioned audio objects, but just to bring a bit of definition there, when I say that, I say it to mean we're looking at a sound source which has some kind of audio content, but importantly, it's got a position with it. And then we may also have some metadata there that provides other information as to what that source is. Does it have any specific directivity which needs to be taken into account in the renderer? How long, what's its duration? And we can look into all sorts of other kind of statistical methods using some of the MPEG-7 descriptions if we want to. But primarily, we're looking at audio content and position. But the beauty of this technique is that we can build on it by allowing this additional metadata. A sound field, I'll define it as a representation of the spatial variation of sound in the given space. So generally, this is for your sort of ambient environmental sound. It gives you that impression of envelopment, we'd say, so that you feel part of the scene. Just having the discrete audio objects isn't enough for you to feel part of the Royal Albert Hall or to feel part of the football scenario. But it's very important, and it allows us to produce either in a 2D plane, or we can do a 3-dimensional sound field, so you get that additional height information as well. So once we've recorded and transmitted these audio objects, they can then be decoded at the user end depending on what decoders they've got. So you're doing your processing, you're doing your mixing all the way at the user end, and you can render the sound scene based on what you've got, whether it's stereo 5.1, Ambisonics, or even wave field synthesis. So we can go, it's completely scalable right up from listening on a mobile phone right up to the most insane loudspeaker system that the human mind can conceive. So that's your audio objects, and it's actually an easy matter just to move those around. And the same with the sound field. By encoding it in specific formats, it allows us to rotate them. So if you're viewing that particular part of the panorama, we can completely rotate the sound field around you. So it's sort of like you're actually in the crowd moving your head, basically. It should sound very similar. And if you're looking in one particular direction, the orchestra's here, then you want it to stay in the same place as if you're actually in the room. And that we can do, providing we can format and broadcast our sound field in the correct manner. So, I think I mentioned much of this in terms of the interaction and having your correct coordinate system, allowing that panning and zooming, and then we mentioned about the sound field rotating as well. So in terms of FascinatE, our audio system is starting to look like this. So what we do is, the important part is we've separated, as you'll notice, the capture part of things where we're capturing our audio objects and sound field. We've separated it from the scene composer and the scene presenter, and then obviously we've got our different sound systems. So just to break that up a bit, our scene composer and the capture side's dealt with here. So I mentioned in the talk this morning about how we go about capturing the different audio objects and the sound field. So that's the kind of raw information. There are audio jigsaw pieces. Then the scene composer basically deals with putting the scene together. So it could be that it uses parameters like the gesture control that Javier will be speaking on in a minute. So looking at the navigational view and then composing the scene accordingly. Or you'll notice these scripting parameters, which could come from, say, additional metadata, or it could be the result of some producer, a local producer, putting a scene together, giving it to the scene composer. So out from that, we have our sound sources with the correct positions. So as you rotate, the scene composer will put the audio objects in the right place and will rotate your sound field for you, which then gets fed happily to the scene presenter, which could be on the same machine, or it could be on an entirely different machine, which deals with our kind of encoding and decoding with lots of arrows, with all the different possibilities. So you see we can we can encode it with this Ambisonics format, which can then be decoded either to whatever loudspeaker setup you've got, really, whether it's a lower order Ambisonics, the same order, wavefield synthesis, stereo, binaural, or what have you. And currently we've implemented the wavefield synthesis rendering, which will be on display at the May demonstration, and the Ambisonics, and many things in between. And obviously, to feed into this stage, you need to know your device parameters. So the user puts in his or her loudspeaker coordinates and what kind of system they've got. So just a brief view now on what sort of sound field descriptions we're looking at. When we talk about a sound field description, we want to know basically what signals we have to give our loudspeakers in order to reproduce this sound field, so that we can do this customized view. So physically, how do we drive these loudspeakers to reproduce it? So we'll look briefly at some of the theory of wavefield synthesis and, as I mentioned, some of the higher order ambisonics. Wavefield synthesis is an interesting audio technique, I think, because it's kind of like, it's like a child thought, what's the most incredible way you could ever do surround sound? Let's try and do it. So this dates back to the 1930s, I think. This is an idea that was originally had by Steinberg and Snow, these guys. They thought that, why don't we just line a stage with millions of microphones and then line somewhere else with an equal number of loudspeakers, and that way we'll capture all of the acoustic information that we need in order to give the listeners every single bit of audio information that they need in order to perceive the scene wherever they are, which is a great idea. You can see these microphones at the top capture the sound perfectly, and then it's reproduced and you get the exact wavefronts, and it's those wavefronts that your ears use in order to piece the sound scene back together again. So great idea in theory, wasn't really implemented because nobody could physically implement the system, basically, especially not with analog electronics at the time. It really cried out for somebody to come in and give it a bit more theoretical oomph. And that was done actually in the 1980s by some guys in the Netherlands who built upon the theory from Christian Huygens, who basically said that if you've got any wavefront, then you can approximate each point on that wavefront as the kind of a position of a new source emanating out from that. So you can see that these wavefronts here are made up of lots of different mini wavefronts, if you like, wavelets. And that's useful, and you can use this fancy equation to figure out what pressures you need what loudspeaker signals you need to produce in order to create one of these wavefronts on an arbitrary sized shaped volume, as is shown here. So these are monopoles and dipoles, because that's kind of like the theoretical basis. If you want to know more about the nitty-gritty, then come and grab me afterwards. But the fact is that we can now determine what loudspeaker signals are needed in order to recreate any wavefront, which means that we can position sources anywhere in space and produce the right wavefronts accordingly. So these audio objects fit really nicely. That omega there, that's essentially one of my audio objects, and I'm producing the wave field that you can see with the dotted line really accurately, so that it will be perceived in the correct position. And you can imagine that being done with multiple sources. So a couple of little animations just to prove that it works. I don't know if it proves that it works, proves that MATLAB can make it work. The interesting thing about wavefield synthesis is that you can make a source sound like it's coming from inside the room. You see that one on the right. So I'm basically focusing all the energy onto one location, and then it re-emits its energy from there, which is incredible sensation. So it means that by doing this object-based approach, you can actually have sources that are in really close proximity to the listeners. So it will give you that sense of presence and immersion more than it would, say, in another system, because you can throw things at you throw audio objects at the person. They can be right in front of their face almost, which is one of the more unique aspects of wave field synthesis. Problem is, obviously, as is shown in this picture, which is our wave field synthesis system we have here at Salford University across in the Clifford Whitworth campus, is that you need lots of loudspeakers in order to do this. You need lots of control sources in order to reproduce this sound field accurately. So that's a disadvantage, but the advantage is that you have a volumetric solution there. So it doesn't matter where you are stood, say for this one on the left, doesn't matter where you are stood in the room, you will perceive the source coming from the correct location. Whereas other techniques such as stereo, they have an associated sweet spot. And the moment you walk out of that, you'll find that your source position will vary slightly. So obviously if you're interacting with a scene and you come to zoom right in, then not standing in the sweet spot could be a significant issue to you as to whether you're perceiving the sound in the correct position. So wave field synthesis has some big advantages there, but is a hardware headache, shall we say, in terms of getting those audio channels. I'll now take this opportunity to hand over to Holger Kropp, who will finish this off, and I better do the mic.
Does this work? Yeah, I think so. Okay, ladies and gentlemen, I welcome you to the second part. I will go on with higher order ambisonics, and the first assumption, in contrast to wave field synthesis, is that we have to deal with plane waves instead of spherical waves. And it looks like this. If you have a sphere and you have a plane wave coming from above, the main goal is to reproduce the same wave behavior on the sphere. And this is what we have to be performed with sound field description. And therefore, due to the spherical, due to the sphere structure, we have to deal with a spherical function, so-called spherical harmonics. And this is the simplest one. Sorry, I need the laser pointer. This is the simplest one here with order 0. We have a parameter called order. It's very similar to if you look onto an AD converter. The accuracy improves if you increase the bits, the number of bits, and here the accuracy increase if you increase the order. So this is the simplest one. Then the first order looks like this spherical harmonic, and it goes on and on. And the difference between ambisonics and higher order ambisonics is ambisonics work with orders 0 till 3, and higher order is more than 3. So this, for example, is the spherical harmonic. It's more complicated for order 4. So if you superpose all these spherical harmonics for a specific direction, the accuracy, how to describe a wave on a sphere could be increased. And the mathematics behind is here given by an example where we have one source from a specific direction, and it leads to a so-called two so-called Ambisonics coefficients. And if you combine all these coefficients here, you get a vector. And this is what I like to explain. I start with the order 0, so you have the spherical harmonics I was talking about, and you have a specific direction, and the direction always stays still, and you get a value for this direction, and the only thing you have to do is you have to multiply this with the incoming, with the signal of the sound source. And then you will get the first coefficient here. This is a very simple one, and as already mentioned, it becomes more and more complicated. So this is order 1. You have there not 1, but 3 coefficients. So in total, you get 4 for order 1, and so on. So if you go on with higher orders, you get, for instance, for order 4, you get 9 coefficients. So in total, you get 25 components. But this is only one single direction. If you consider different direction, you have to combine all these. This is the vector of one direction, and if you have more than one, you have to combine all these separately, and you get the total vector of all possible source directions. So this term stands for each source, for one source. And what you get at the end is a very simple matrix vector multiplication. This is called the higher order Ambisonics encoder. Okay, this data can be then transmitted via IP on the output side. And on the rendering side, you have not to deal with the source direction anymore. You have to deal with the available loudspeaker direction, and they are different. So what you have to do is you first have to invert the encoding step, but under consideration of the appropriate driver signals for the loudspeakers. So at the output or the rendering, the main task is to find this matrix here, the decoding matrix is it, and then you can reproduce the driver signal for the loudspeakers. And this is the main task. So here is an overview. How does it look like? On the capturing side, you have different microphones. You get not only one, but a lot of source signals combined to a vector. This can be multiplied on the Ambisonics with the Ambisonics encoder matrix, where you consider the source positions, and then you get an intermediate state, which is called the Ambisonics vector, or the Ambisonics coefficient. And to reproduce this, you have to perform the inverting step. You have to use a matrix or you have to perform a matrix vector multiplication again. And then you hopefully get the driver signals on the output. This is what Ambisonics does. So simplified view is that it is a matrix operation which allows a superposition of all these directions. But another advantage is due to the use of spherical harmonics, because they are rotational invariant, you can also perform a very easy rotation. And this is very useful in the FascinatE project if you consider the panoramic view and the audio which follows the panoramic view by rotation. So now I want to show you, I want to go more into detail concerning the implementation. And I start first with the production side, very short. As Rob already mentioned, we have the audio objects, which is simplified as signal and position information. And for the higher order ambisonics, we have to record the ambient sound, and this can be performed with a specific microphone, a spherical microphone. But furthermore, we can also include some virtual sources into the ambient sound, or we can also mixture the audio objects if we encode it on the production side. So we have in the FascinatE project a mixture of audio objects and Hoa-based encoding sound. And this is a typical spherical microphone we use. It's called an Eigenmic from the company MH Acoustics, and it captures the sound on this sphere here. And it has 32 capsules on the sphere, equidistant. So you get 32 different channels which are sampling the ambient sound. But now you have, in a first step, to perform an encoding, and due to the number of 32 channels, the next possible order would be, is 4, so that you can deal afterwards with 25 ambisonics coefficients. Okay, this is a very useful microphone, but you have also some problems because it's a kind of a spatial filtering. For instance, due to the restricted number of microphone capsules, you have an effect called spatial aliasing. And this, because it's a fixed microphone, you cannot correct it. This is not correctable. And furthermore, here you can see the SNR, or the power of the array response on the rigid sphere. And what you can see here, this is the order 0, order 1, and so on. And what you can see here is that the higher the order, the more noise you get. And this can be modified. And we do this by a specific noise reduction filter in order to equalize these characteristics. But this has to be performed before we do the encoding step. So after encoding, we get 25 components that are transmitted, and in the FascinatE project, we try to transmit this via a TCP transmission. And here's just a few words about the data transmission we or the performance we have to meet. 38 megabit per second for 25 coefficients, plus some data amount for the audio objects. Furthermore, there are some controlling parameters like loudness, mute, the order, positions, and for instance some rotation data if you like to have post-production where you want to rotate the field. So in summary, we have on the capturing side the audio objects. By object extraction, you get the positions and the spherical microphone with an processing part afterwards where you encode these signals. This can be then transmitted via TCP to the rendering side or the reproduction side. And the first step we have to perform is a separation of wave field synthesis and Ambisonics encoded data. So this is the first step. Rob already mentioned it. It is performed in the audio capturing. And then afterwards, we have we must get back the loudspeaker signals, the appropriate one, and therefore we first have to perform a decoding where we first have to invert the encoding step, and then we have also to consider that the source position are in general different from the loudspeaker position, and this is another signal processing step we have to perform. So here's a typical example for possible rendering situation. This is a 3D setup which we have in our lab. It's for small room events like football or something like that. And it contains on 16 loudspeakers. You have 8 here on the horizontal plane, and you have additional 4 on the top in the corners and 4 at the bottom. You have seen maybe already this loudspeaker setup in the demo outside. And the problem you have here is this is the real position, but this is not an ideal position on a sphere. So this is why I was talking about the additional signal processing step. So where you consider the different position. And also, if we like to map onto stereo or 5.1 formats, this requires an additional step, and this can be done by an adaptation which we call panning. Okay, but we found out that even for order equal to 3, we get a very impressive live feeling. Maybe you already heard the demo with the Chelsea content, and it is nearly realistic envelopment. Okay, this was already mentioned. On the rendering side, we have the scene composer in order to separate audio objects from the encoding stuff. And here is the possibility that if you want to encode also the audio objects via the encoding, the additional encoding in the last step here of the presenter. And if you want to drive the appropriate loudspeakers, you need the decoding step here. So the encoding and decoding is the most challenging task in our case. Here is our software tool as an example, where you can deal with normal files. You can use pre-processed matrices, but you can use also real-time encoding and decoding in real time. Okay, this was just a possibility. Now I will summarize this talk. We were talking about the spatial audio in the FascinatE project, and Rob mentioned why we call this format agnostic approach. And he was introducing wave field synthesis, and I go on with higher order Ambisonic and showed some capturing and rendering possibilities. And we think in FascinatE we have the possibility to capture, transmit, and rendering a realistic 3D sound in the whole environment. Thank you very much.